most of the people don't realize that this is like already happening, especially over the past few months. In almost every lab, the new generation of the models are built heavily using the previous generation of the models. What is missing right now is long horizon and full automation. And we're moving to that direction super, super fast. The moment that we have this full automation, we can close the loop of self-improvement. We just got rid of the human bottleneck for improving these models, which I expect to see a huge jump again from such development.
Hi, I'm Matt Turck. Welcome to the Matt Podcast. Today, my guest is Mostafa Dehghani, a top AI researcher at Google DeepMind and a core contributor to some of the most influential architectural breakthroughs of the last decade, including universal transformers, the vision transformer, and the natively multimodal Gemini family. In this episode, we unpack what's hot in frontier AI right now, including what it actually means for AI to think in loops, and the immediate timeline for recursive self-improvement, where AI autonomously builds the next generation of AI. We also dive into the technical evolution of image generation with Nano Banana 2 and why continual learning could completely disrupt how enterprise data pipelines and RAG systems are built today. Please enjoy this fantastic deep dive with Mostafa Dehghani. One of the hottest concepts in AI research right now seems to be the concept of loops. So I thought it'd be a fun place to start. This idea that models are going to improve not by being bigger, but by thinking recursively. What does that mean exactly?
Definitely one of the toppest active areas for almost every lab to invest in, looping, and it has like operation at different levels. The one that is on the macro level is basically the looping that we use like architecture or at inference time for test and compute and stuff like that. And then at a higher level is basically the loop that we have over the development of these models, which is basically we refer to it as self-improvement. If I want to put it like let's talk about self-improvement as like this general concept, right? Like if I want to put it like very simply, it is really just the continuation of the trend that we've been like riding for decades, right? And think about it in classical machine learning. Humans had to sit down and manually engineer the features, and you had to decide like what the model actually pays attention to. And deep learning and neural network came along, and they said, okay, let's just remove that. Let the model figure out the representation itself. And that was actually a huge deal. And we somehow removed a massive human bottleneck and human bias. And then like further, and instead of just like hand designing architecture, we started learning them to, instead of curating like, every piece of training signal, we scaled to kind of basically data-driven approaches and let the data speak. And the self-improvement and this like loop into development is just the next step in the same direction. And the whole idea and the whole point of it is you're removing the human bottleneck and bias from improving these models, right? And now, like you say that, okay, not just human doesn't have to handcraft features anymore, but also we don't want the human to sit in the loop every time that the model has to get better. And I think that's basically on the development side. So it's not radically new. It's the same story, just a new chapter of the same story. I think every time that we removed human from like human judgment from this process, we kind of got over a bottleneck. I would say like this self-improvement and looping over the development is kind of like doing that at the highest level, which is basically improving these models. If we want to go to more detailed level of looping, we can talk about ways of increasing test and compute for these models and how we let these models to loop over their process within a specific problem to refine it, to think about it. And I think the most familiar form is just like chain of thought and letting the model to think with extra tokens. That's beyond that. And you can think about different ideas that you let the model to increase the compute for any specific problems. Like what if I have like dummy tokens that they can use as like read and write tape to kind of like, verify what I've done and go through the solutions or the process that I'm like doing over different steps and understand, like what has been done wrong, what has to be done next, or even like, negative sparsity, which is basically reusing part of the model multiple times. And this sort of looping is also like been shown to be super, super helpful, mostly because you just let the model to throw more compute on a difficult problem.
So that's self-improvement at inference time. I think you alluded to earlier, there is also a bigger concept that's maybe I guess more science fiction, except it seems to be becoming a reality very quickly, which is this concept of recursive self-improvement or RSI. That seems to be what a lot of people are talking about. I think ICLR is coming up in a few weeks, and there's a bunch of papers focused on that. So what is that? What is recursive self-improvement as a concept?
It's actually interesting because you referred to that as something that looked like a bit of a sci-fi situation where these models are actually improving themselves. And that's true, because a few years ago, when you wanted to talk about this, you could just write a perspective paper at a conference and talk about it at super high level. But if we go and check out what is happening right now, to a really good extent happening, most of the and it's somehow most of the people don't realize that this is already happening, especially over the past few months. In almost every lab, the new generation of the models are built heavily using the previous generation of the models. I think that's basically the case again everywhere. And it's not fully automatic yet, but the direction is super clear. And it's easy to imagine that, we're going to get to a situation with full automation. These models are going to improve themselves and keep learning from the world. And again, it has relation with other concepts like continual learning and other concepts that we are still not yet to the most advanced point of it. But if someone comes and say that, I have an idea to get a model to calculate the gradient and updates its weights on the fly, it just feels very normal. It's not something that, wow, this is such an amazing idea. I think what is missing right now is long horizon and full automation. And we're moving to that direction super, super fast. The moment that we had this full automation, I would say we can close the loop of self-improvement, and then it becomes the problems become mostly providing compute for these models to actually do what they want to do. And as I said, early comment, we just got rid of the human bottleneck for improving these models, which I expect to see a huge jump again from such development.
So people may have seen or heard about Karpathy's auto-research project a few weeks ago. Is that an example, presumably reasonably narrow to make it work? Is that an example of a self-recursive loop?
That is, definitely. And I think that was one of the early examples of
seeing these models actually doing something super sensible on the research side. So we've been seeing them doing a lot of good work on improving the engineering part of the development loop. But on the research side, which you think about, maybe some sort of gut feeling or intuition is needed, and a researcher with a long time of playing with these models and experience can do this, but not necessarily a model. I think we're seeing the sign that maybe basically that kind of golden part of the recipe, a successful recipe that mostly coming from intuition of a good researcher, is coming to kind of these development loops by these models. And it's a bit hard to think about, does it mean that we can replace every genius researcher with these models very soon? Maybe, and I don't know how soon, but this is definitely a sign of something that we kind of doubted a few years ago. We couldn't believe that, wow, this is going to happen that early, which is very exciting.
I want to play it back just to make sure that people listening to this understand. I mean, we're talking about AI building AI. And I think a few months ago, if you talk to researchers, people would say, oh yeah, we already use AI to build AI, but that really meant that we use AI tools and reasoning models to come up with ideas and thoughts about building models. But here what we're talking about is AI automatically updating itself, updating its weights in a recursive manner, leading to potentially a dramatic acceleration in progress. And what you're saying is that this is largely upon us and a question of longer horizon and basically more compute. Is that fair?
I think so. This is one. And the other one is also, I'm not going to say that, soon we're going to have these models fully automated. And there are actually many problems that we have to solve. But directionally, I can see how this can happen. It's not something that I would look at it as like super hard. It's like hard, but very possible.
Okay. So what are the roadblocks? So you talked about compute. Is evaluation one of them? Because presumably the model needs to understand what is right and what is wrong in terms of the quality of the answer. Is that one of the issues?
100%. At the end of the day, you can only improve what you can measure, right? And then getting evaluation is like just hard. And at the end of the day, it becomes almost a philosophical problem, not just a technical one. Like, this is actually a very interesting observation. So if you have a team of super competent people, most of the time they can do like massive progress on a problem if there is some concrete eval to heal climate. But if there's no eval, it's just like really hard to make progress. And the fact that we don't have evals that or like even defining evals that can maybe measure, how close we are to the point that we can actually get a self-improvement loop. It's just like we don't have that, and it's just making it like much harder to measure the progress in that direction. But there are proxies, and there are definitely some evals that like we're going from. Maybe we can evaluate like every step of the model toward this direction, and maybe we can evaluate up to this many turns of the model, or maybe we can evaluate the model helping itself to improve in that specific framework and in the specific setup, and this part of the machine learning that needs iteration. It's also quite interesting because the difficulty of building eval is like the infrastructure that you need to reliably run evals that are super complicated is also like super hard. It's quite funny, but sometimes figuring out that, okay, how can I create an environment for a model that operates safely in like within Google, right? And does all the jobs that an RE and like a RE, like research engineer or a research scientist can do, like in a safe setup, where they can because right now we're not confident about, them doing the right things all the time, and measuring like how much they can push and how long they can push a task is very difficult. And like connecting all these points into an environment that these models are operating, and then get them run efficiently and like bringing diversity to eval is definitely one of the bottlenecks of like making progress in this direction.
A couple of weeks ago, we had a fun conversation with Karina Hong of Axiom Math, and we talked about formal verification. Is that a promising area from your perspective? Is something like formal verification what would enable you to make sure that the improvement loop keeps continuing?
In my opinion, formal verification is one of the most powerful like keys to enable like self-improvement, but it's not the key. And if you think about it, like for math, code, logics, it's great. You can run a proof, either it checks out or not. If you go to other domains that are a little bit messier, like for example, you cannot write a formal proof that if a doctor's recommendation is good, right? Like so it's not hard. It's not easy to have like to extend this formal verification to all the domains in real world. But one question that is actually an interesting question, which is very relevant to formal verification, is how can we look at these methods and like formal verification and build that kind of tight and honest feedback loop for the messy part of the work. I think that's like very inspiring to build like on top of these like formal verification methods to extend to domains that like not easy to verify easily, but you need some sort of clean and tight feedback loop to be able to make progress.
So same problem as reinforcement learning, right? Like the second you start veering away from math and code, you start getting into like very messy territory. Is model collapse one of the issues to think about, or is that orthogonal?
Model collapse is definitely a risk, right? And I would say model collapse mainly happens when you have a loop that is completely closed, right? And if you don't have any outside signal, and just the model, for example, talking to itself or operating in a very like a restricted environment, there's a good chance that your model collapses. But if you have a strong verifier or some sort of a real reward signal that anchor this kind of like signals that is coming from like AI generated data, for example, it can be quite powerful. I think like the key here is to stay grounded to something real, And then you can most likely avoid things like model collapse. And again, it's a risk, but it's not definitely a major blocker.
And perhaps to make this accessible to everyone, can you define what model collapse is in the first place?
So basically, when you have some sort of data and environment that these models are interacting with, but those environments and data are designed, for example, by another model. Like this is just an example of that, right? And then you become really, really good at this specific part, and then suddenly you lose generalization to anything beyond that. And this is one of the kind of definition, or one of the cases that a model collapsing would result to.
So you mentioned losing generalization. Is that particularly in the concept of RSI a worry that either you have those self-reinforcing loops, but they need to be fairly narrow, or you have more general models, but then you kind of have the loops?
This is an interesting question. Again, generalization versus specialization. Let me go a few steps back. We had this discussion many, many times. How should we do a trade-off between generalization and specialization when we are developing these models? I think long term, you want a model that knows everything and knows when to go deep versus wide, right? Imagine you have an agentic actor, right? If you're an agentic coder, if your agent is super strong at every step of operation, a really, really good programmer, it's amazing, it's super specialized. But for many of the problems, coding problems, you need some sort of planning and understanding what's going on and collecting information and based on the context, deciding what to do. And then after you define the steps, then your super strong specialization just kicks in. And before that, being a generalist is super useful. Definitely generalization is one of the things that you need to get to the ultimate side of AGI. But short term, I would say building a specialist model is probably the fastest way to learn what is actually possible. And in many cases, these specialized model are becoming a stepping stone toward a generalist model, which is super valuable, right? So you can imagine that, if I'm actually thinking about self-improvement, maybe I need to make sure that, in a very specific area, I can build that. Maybe, I focus on coding, and then if it works out, then I go through how to widen that and how to bring more into this specialized setup. One thing that I always say is that people don't care what category their problem falls into, right? And if a human calls something a problem, then AI should be able to solve it. And I think that's fundamentally a generalist need, right? So at the end of the day, you need generalization, and playing this, going through this spectrum of super generalized model and super specialized model is more about a long-term, short-term, and how to take advantage of each side during this process.
What's a specialized model today? Is that a separate model, or is that a broad general model that's trained in a specific way, including in particular through RL?
Okay, so here's the point. We used to have constraint compute, and then if we wanted to push a model to be so tall, we would choose specific dimensions, and then we say that, okay, we want to kind of allocate the compute that we have to that, and then make this model really good at this, something that is extremely expert at this. So that was basically the trade-off that we were trying to make, given the compute budget that we have. As we go through this the phase of compute becoming more available, cheaper, and then maybe we're constrained with other stuff data and stuff. One of the other trade-offs that pops up is, especially in post-training, this game of evacuable, that sometimes it's really hard to get your model to be good across the boards. So you try to kind of make it good at something multimodality. Somehow you see some regression on the coding, and you make it good at coding and multimodality. It becomes a little slightly worse than a model that you had at math and reasoning. So it's hard to kind of find a balance. And part of it is because post-training does a little bit of a overfitting, at the end of the day, when you post-train a model, you are trying to overfit it to the best local optima you have. When recipe becomes how can I find the best local optima? It becomes the problem of, okay, there's no local optima that is good for everything. So you need to kind of choose, right? And then like seeing this, you end up with like making some decisions along the way and saying that, okay, maybe for me at this stage, because of the need that I have in my organization, like with respect to the competition that is going on, I need to choose, this specific axis. Like, for example, some companies have like a very strong focus on coding, which is, okay, I make my job like super easy, like, or not super easy, but like much easier than the competitors that they want to basically ship a model that is good across the board. I think short term, it's like very, very effective because first of all, during development, you care less about, like all the dimensions. So maybe it's just faster to iterate. Like you kind of free up some space from the mind of your researchers and engineers that, okay, like forget about this. Just let's push this to the max. And then the other one is also like you don't hit the trade-off like immediately. And especially this model is that like, okay, I'm going to pick this specific axis and then make the model like really, really good at this. Sometimes, again, like this is a decision based on the place that you're at, again, like organizationally, like competitors, like, and stuff like that.
Great. You said something a few minutes ago that I thought was so intriguing, which is this idea that the Karpathys of the world and you of the world could be automated. What happens if like the brightest minds in the world get automated and the AI creates itself? Like at some point, is there just no one knows how the AI works? Is that an actual possible future?
This is actually very philosophical. I don't know. Well, let me give you one quick things that I thought about it a few days ago. I have a daughter. She is like 1.5 years old. I've been impressed over the past few years. Like very interestingly, like I've been proven wrong multiple times about like the timeline that I had in mind. For example, sometimes I say like, oh, this is going to happen in 6 months. Never happened. Sometimes like, oh, this is just like so hard. Like within the next 10 years, there's absolutely no chance to solve it. And then boom, like in 2 months, 3 months, someone had a brilliant idea and they solve it. So it's like really hard to predict the future. And I was thinking like, okay, like, so you're talking about like Karpathy and like, again, like other researchers, but I'm thinking about, okay, like what about the next generation? If like my daughter at some point comes to me and asks like, okay, like what should I do? Like what do you recommend to study? Like what major and like, what branch of the science or research should I kind of like, dig in and like be the expert on? I really don't have a good answer, like almost it doesn't exist. And it's just like really hard to predict the future. What I know is there are a few skills that are probably key to be able to make impact in this world and also be relevant, staying relevant. Like one of them is like a strategic and having all the parameters on your table when you're making a decision and becoming an absolute expert about a very specific subject most likely is not going to be useful in like the near future. I think like, the brilliance of Karpathy is not like, he's a good programmer or definitely he's a good teacher, but I'm saying like, these are not like the most impressive part of it. Like the most impressive part for me is that he has a really good overall view of like what is happening. Like by putting himself in the like the stream of information, he can make a decision about, okay, what is the next most impactful thing to do? And now, like, the things that he does to make impact is very different from like, the things that he used to do like 5 years ago. And I think he can be able to do that, like continue doing that, like what is that, the things that he's going to be doing like in 5 years, I don't know, but I know it's like he's smart enough to figure it out and still keep making impact on the board.
So AI researchers are not researching their way out of a job just yet.
Hopefully we are smart enough to do that.
All right. Maybe that's more of a macro question as I think about, where the value lands in this ecosystem. But if AI just keeps creating itself, then is data still needed in that equation, or is that all compute?
Concept of data is a little bit like broader than just like, tokens, right? Like, and if you think about data as whatever that the model can get signal from, either it is like predicting the next token in raw text, which we kind of like, use in pre-training, or super complex environment that the model interacts with and then gets signal. This is something that basically like we can like refer to it as like data, right? And it's not like data or like the value of like having good data or working on data is going to disappear and compute is going to become like the only things. At the end of the day, I think like the work that we're doing on the data side most likely is going to shift toward building environments or making sure that these models can interact with physical worlds. And then it becomes more of a problem of, okay, how can I like provide more grounding for these models? They are good at like improving themselves, but as long as like, you know, I expose them to real world data, right? Like, and like, you know, real world environment. So providing data becomes more about, okay, how can I give access to this specific like model to something that, you know, we never had. For example, again, like something came to my mind, which is like, again, like a little bit sci-fi, but how can I make like smell accessible to these models? You know, like right now it doesn't, like there's no good way, but then data becomes like, okay, you know, like information or anything that is for us because of all the sensory that we have is like really easy. You know, like right now I'm sitting here. I know how hard is my chair. What is the temperature of this room? All this sensory information is something that is coming to me. And then I'm like, the next word that I'm saying is based on all this input, right? And then providing this for a model that does self-improvement is already a really hard problem. So I would say that the work on the data would shift toward making these sensory information more available to these models in a way that it enables them to really improve themselves, given all this information in a more effective way.
Yeah, interesting. Yeah, there seems to be a big trend towards sensors as a service. We're seeing the startups emerge in that field. Okay, super interesting. Zooming out from self-improvement for a second, the big theme of the last year has been the acceleration of post-training in addition to pre-training. So the whole reinforcement learning aspect of things. Where do you expect gains to come from in the next few months or year? Is that more post-training? Is that more pre-training? Is that both? Is that something else?
The answer to this question really depends on when you actually ask this question. And like, it's obvious that like, you know, we're going to be having a bit of a swing back and forth between pre-training and post-training. At the end of the day, I want to say that, you know, pre-training is still the foundation, and like you can never post-train your way out of a weak-based model. But right now, the current, like the return on post-training is really strong. And I started working on post-training myself like a few months ago, like Gemini post-training. Like mostly coding and agentic. I can see how a brilliant small idea can make a model like 10x better, for example, in terms of behavior at a fraction of the cost of the pre-training, right? This is, again, like, you know, we can see how post-training is like the place to make a lot of impact and improve these models. But on the other hand, like I know at different companies it's also the case, but at Atlas at GDM, a lot of exciting recent work is going into the pre-training side, and like new recipe, new ideas, and I would say, like, you know, the work that we're doing on the pre-training is going to unlock a lot of downstream possibilities. Post-training is just like a different mode of operation. It's like also super interesting for me because I'm, again, like a little bit like new to this side of the operation. But at the end of the day, I always expect to circle like going on, like, you know, between post-training and pre-training.
Your comments on pre-training are sort of against like that narrative that appeared a few months ago that pre-training was dead. That's not your take at all, right? But
I think everyone has ideas on pre-training side. At the end of the day, like going for that idea is a function of complexity and the expected gain, right? And sometimes you feel that, okay, you know, there are low-hanging fruits, and it, like, you know, instead of bringing this complex, like, you know, recipe to the pre-training, the one that I have, like, which is simple, elegant, super scalable, I'm going to push this and then move the effort to the post-training. And then at some point, like the base model becomes the bottleneck, and then you're happy to take the complex recipe and bring it to the pre-training and then like keep pushing it. I think pre-training is dead. I would say, like, maybe, like, you know, the old, it's also like a little bit like difficult to talk about old and new because like the time frame is like very different. So when I say old, maybe I'm referring to, like, you know, 2 weeks ago or something, but the way that we used to do pre-training, maybe like, you know, a year ago or 2 years ago, maybe, like, you know, diminishing return is like obvious, but I can see how new ideas are bringing, like, you know, fresh energy into the pre-training and suddenly just open a door toward like something exotic that might actually drastically change the base model capability over time.
So exciting stuff for Gemini 4 whenever it comes out. You mentioned continual learning earlier, and that's another one of those hot topics that people have been talking about. Can you define continual learning for us so that this conversation is educational for a broad group of people? Maybe compare and contrast that with the self-improvement loop. Like those are two different things, but help us understand the difference.
Definitely they're related, but like they're distinct, right? So self-improvement is about a model getting smarter over time and improving its capability, like the model itself doing it. Continual learning is mostly about a model staying current, right? Like, and think about a doctor that like keeps reading new research and they like refresh their knowledge about stuff, and like, they're trying to make sure that, their knowledge doesn't go stale. The shared enemy between like self-improvement and continual learning is a model with frozen weights over time, while the board is just like going, right? Like, if you have a model that is just frozen and the board is moving, then like you neither get like self-improvement nor continual learning. But continual learning is mostly focused on making sure that, if there's like fresh knowledge in the board, like the model knowledge cutoff is not in the past. So it's constantly, like, for example, overnight, all the news, everything that is happening in the board, everything is just like, updated. So if today you ask a problem, if you ask a question from the model, those knowledge, which is like super fresh, is already in the weight of the model. So it doesn't have to kind of like, depend on external source to bring it in. And it's hard. It's like really, really hard. And the biggest problem, like not the biggest, but like one of the big problem is like catastrophic forgetting, where you get your model to learn about new information after you're done training that model, like, and then and suddenly you see regression in the knowledge that you learned already in the main training phase. And it's a very active area of research right now.
And what's the reality of continual learning as of now? Is that built into existing systems? Not at all about to?
There are two sides of it. Like one side is, I think like the research is not like yet to a very like to a point that you think that, oh, this is the recipe, I just need to kind of like, exploit it and push productionization, right? But basically, like every time that you have a new problem that is like key, you have this phase of exploration where people like try to kind of like, try different ideas and, like go jump over this like idea to another idea, which could be like so different. And then when you're confident about this kind of working to some extent, you go to the exploitation mode and say that, oh, let me just make it as good as it can be. And, this is the way to kind of push it and let's scale it. Let's just like, develop infra for it, make it like super fast, like, productionize it and see what happens. I think like that is not yet there. The other one is also, again, like, as I said, because we never had like super confident recipe for continual learning. Like building infra for it and investing in something that is like fast is hard. Given that, I've seen like very impressive progress on this of this within GDM. It's kind of interesting because it is one of the things that it can be heavily theoretical. I've seen people who are like doing a lot of theory work and they got into this like problem and they're having a lot of fun and they're also like making a lot of impact. And it's impressive how much progress we made on this. But I don't think that we have yet like any idea that like everyone says that, oh, this is it, like, let's just do it, like, let's push this.
Great. I'd love to talk about you and your background. Tell us your story in a few minutes. Like, how did you come to do this work and what was your journey to AI and then your journey to Google DeepMind?
So I did my PhD at the University of Amsterdam on machine learning and mostly on the like the language model side and text and search and retrieval. And then I think what kind of like pushed me toward trying really hard to be on the on the mainstream and be part of this group that are like hustling to make like really good progress. I did a few internships like back in 2016 and 2017, and the funny story is I did an internship at Google Brain in early 2017, and then it was amazing. It was just like I went to this team. They were working on like LSTMs for summarization. Summarization was actually one of the most like interesting problems at that time. I was like amazed. I was like, so this is so good. I just want to keep doing this for the rest of my life. This is it. And then I got a return offer to go back and then do another internship at the end of the same year. The recruiter told me that, there's this team that they just published a paper, maybe you've heard about it, like Transformer, and then they're looking for an intern. And I had a chat with, I remember I had a chat with Lukasz Kaiser. And then Lukasz was talking to me and was saying like, they have this idea of building like a Kolmogorov machine based on Transformer, and he was so excited about this. And then we finished the conversation, and I started sort of sending a message to a recruiter. And I was like, I don't know if I want to go with this team. It's just like they're doing something random. Like everyone's doing LSD. I'm like, why should I go and work with a group of people who are working on this like random architecture, like Transformer? It's just like it's gonna die, And then he tried and he couldn't find any other team for me to join. So I joined this team as an intern, and that changed my life. Like being among these like super brilliant, like super smart people that they believed in some vision and direction, where almost everyone was excited about something else, was like very inspiring. And then we work on like, again, like this Kolmogorov machine like idea of which turned into like, universal transformer paper, which, like recursion in depths and reusing parameters was coming out of it. And still they like making a lot of impacts after almost like 10 years.
Tell us about that quickly. So that was in 2019, I believe, and you were a co-author of that paper. And that was very much that idea that we started with right at the beginning of this conversation of like loops and recursive stuff.
So universal transformer, like we wrote that paper in 2018, and I think it was also rejected one time from one conference, and it was accepted in 2019. I don't remember exactly, but yeah. I think it was accepted iClear, but it was rejected from NeurIPS or something. The whole intuition was there is something about reusing parameters and a model going through its output another time, and so basically you generate something and then you kind of like, pass it into the model again, and then the model has the chance of doing this. So we started with like, I remember Lukasz had this like algorithmic data set, which I remember he used to call it like algorithmic tasks. And it was part of this code base based on TensorFlow, like tensor to tensor. It was the name of the code that's still there. And I remember I can even find my pull request into that for pushing the universal transformer code. And we saw that basically there are some problems like copying an input to the output, or, like doing something algorithmic with like super long input on the output side, which is super easy, but the normal models, like the normal transformer, was like failing awfully at this. And we saw that, like looping is like do it perfectly. And then at that point, I remember we had this baddie like data set from Meta, and it was like doing great on that. And then the idea of test time compute, which basically you train with fixed amount of compute, but at test time, you unleash your model to do more computation, throwing more flops on the input, was coming to our mind. Like super excited about this. And then we ended up with actually kind of like introducing this adaptive computation mechanism into this, which was again, like some sort of inspiration from Alex, like Alex's paper, like, from LSTM. And then like a very interesting ride, because we were pushing for something that like at that time, it sounded exciting, but and I have a guess, like maybe at that time, like the whole field was a bit too focused on using adaptive computation for decreasing the cost on simple problems. But now we know that maybe we can actually use adaptive computation to increase the cost for hard problem. It's actually like the other side of the same coin, right? So because at that time we were like, like maybe, like resource constraint and everything. So we were really thinking about why we were spending so much flops, like, going through all the layers, and like, everything's for dot, like at the end of the sentence, if that token is like, do we really need like 24 layers? So how we can decrease that? But now we have a different perspective to that, which is like, how can we increase this for a physics problem that we want to run the inference for maybe like, for 2 weeks. So that was really fun to work on that with these like brilliant people. And I think like, just like recursion in depth and reusing the parameters, or I've seen later, like some people actually framing it as negative sparsity, which is a great way of, like connecting it to mixture of experts, that, in mixture of experts, you have flops-free parameters. So parameters that they're not actually bringing any flops. And in like looping, you have parameter-free flops, where you don't have extra parameters for the extra flops that you're throwing on this. So it goes the other direction of the sparsity. And it's quite effective. And I think people are picking it up, so we're seeing a lot of, like excitement in this direction.
Fascinating. Another fundamentally important contribution to the field that you did was the visual transformer paper in 2022. So the paper was called An Image is Worth, 16 by 16 Words Transformers for Image Recognition at Scale. Do you want to walk us through what that was?
There's also a funny story for that. I got into vision and multimodality with that paper. So I've never worked on like any vision problem. It was mostly because I was sitting next to people who were working on vision. So like my desk was like next to people who were working on vision. And that was the reason that I got interested, because I was just talking to them. I was like, oh, this is actually interesting. And then I remember that at that time I was like working on like externally we call it Palm paper with like Akanksha and other folks, and I was like, why we have 400 billion parameter language models, but the biggest model that we have on the vision side is just like maybe 100 million. Like erase that. Like why? Like why there's no benefit of a scale? Started looking into this with folks on like, okay, like maybe, like there's something in transformer that actually kind of like, make it a scalable. And then maybe, like we can move away from convolution to try this. And at the end of the day, I don't want to say that, like that's the only way of scaling. Maybe, if a group actually spent like enough time on convolution, they can also make it a scalable and like, like as good. But there was also benefit of doing that simply because the rest of the machine learning field, which was working on language, they were using this architecture. So they were building infra for it, making it faster, and sometimes the hardware is kind of like designed based on this architecture, at least for short term. So we started pushing, and then I remember that we had a bunch of ideas that, okay, what if each pixel is a token? And then like the cost was going high, the context was just like getting super long, and then we had a lot of back and forth. And it's also quite funny because we started thinking about this problem like from like very complicated point of view. So we were trying to mimic convolutions to be able to get this working. And it ended up like, like I had a bunch of colleagues also in Zurich, and they started like trying the simple idea of what if we just like divide the image into patches of pixel, 16 by 16, and then get each patch as a pixel and forget about, like overlapping patches or, like windows and stuff like it. That's it, like chop the image and then feed it to a transformer. And then scale, like go with a lot of data. And then like, let's start with like, something discriminating to train this model. And it worked. And it was also a little bit like of a surprise for us that, oh, like they were all thinking about something like, fancy and very, very complicated, maybe in the direction of having like, like convolutions and stuff. But something that worked was basically the simple idea of, patchify, fit it to transformer, scale it up, and then boom, you had a really, really good model for representation learning.
Yeah, and to play it back at the highest level, that basically meant that you could apply transformer architecture to image, wherein in the past you had two different families. You had the CNN world and the transformer world for text, and your breakthrough was to prove that transformer could scale equally well to images, which basically paved the way to a Gemini 3 today, which is like a natively multimodal model. Is that,
exactly.
Is that fair? Okay.
Yeah, that is true. Yeah, like so basically we like with that we kind of took a step toward having also videos like adapting transformers and audio like adapting transformers. So basically we like again like even if this is not like the only architecture that would be like multimodal, but it made it really simple to train these models like natively because you have like a single architecture and can have all the modalities during training.
Great. So that's a perfect transition into your work into Nano Banana and the future of image AI. So you are part of the Nano Banana team, and which must have been so much fun when this came out and went just completely viral. And what an incredible product. So since then, there's been a couple of releases. So there's been a Nano Banana Pro in November of 2025, and then just a few weeks ago, Nano Banana 2, aka Gemini 3.1 Flash Image. Yeah, at the end of February. So a lot of people assume that image generation works as a translator, meaning that the AI reads the text of the prompt and then translates it into picture instructions and then draws it. But as we were saying, Gemini is natively multimodal. So how does that work? How does a model actually process the text and the pixels at the same time to build the image?
I think the reason that maybe I got to the generation. Okay, by the way, there's also one thing that I'm not an expert in image generation. Like when I started working on this, I remember I had like meetings with people, and then they were talking about like computer graphic and all the like old like ideas about or like intuitions. And I had like zero idea what's going on. I was like, I know how to train a transformer and scale it, and if it helps, I can basically contribute to this. But again, like it was fun because I worked with like a group of like super smart, like brilliant people with like really good intuition. And I think like the reason that I was excited about this was again, like this is maybe not super relevant to like Nano Banana itself, but to just mention this, I was excited about the idea of like positive transfer across modalities. So when you think about multimodal like natively, one part of it is that, I'm adding capability to my model, so my model can understand images and understand videos and understand audio, but also like and text, but also can generate all these modalities, so I have a model that actually does all these together, right? This is for sure exciting, like from the product point of view, like you have a model that is like, great model for generating all these different like outputs and like users are like finding it like very useful and interesting. But the most exciting part for me was, can I see a glimpse of transfer from these modalities? Like, like for example, if I train a model to become good at generating images, does it become also good at like better at like generating text? There are different intuition of that, like why this should happen. I think there's like something like, again, like very old in the literature on the linguistic side that they call it reporting biases, right? So like you for example, like visit your friend's place, right? And then you go to their place and then you see that they have a banana shaped like sofa. And when you go home, the chance of talking about that sofa compared to a normal sofa is like much higher. So you can actually talk to your friend's partner later. Like, I went there and then their sofa was like in the shape of a banana, which was really fun. But if it was like normal, like you almost like, it's weird if you go somewhere, it's like, by the way, I went to my friend's place and they had a sofa, which was like super normal. So this is the language reporting bias. So language doesn't talk about things that are like at the middle of the distribution, right? But if you have an image or if you have like vision input from anything in the world, you have that information. Like there's no need for reporting it. It's just like there, right? So because of that, like picking up a lot of knowledge about the world through language is just not really efficient. I don't want to say that it's impossible, but it's not efficient. Like to learn about gravity, if you kind of like, have your model train on videos, it's much easier to get the model to learn about gravity because it just happens in a video than training your model on all the textbook to kind of like learn about the concept of gravity, or what is actually gravity.
Is that a concept of world model that's built into the image representation?
Exactly. So basically you want a world model, basically, like these models to be also like a world model. So you want these models to know about the world. Is a good chance that you can actually teach your model about the world just by presenting text to it, but it's just not efficient. And a good shortcut would be to bring multimodality into this. And the best way of learning about a modality is learning how to generate that, right? Like, so we got to this point that, okay, we've been having Gemini generating like images from Gemini 1. So we like basically like Gemini was multimodal from day one. And the reason that we kind of first like released the image generation at like 2.5 instead of, like Gemini 1, Gemini 1.5, Gemini 2, was that it was not great. And then like it really needed a push. And then we figured out that, okay, how to push this without like, introducing any regression to other capabilities that the model has and, like bring all of these natively into the, into like this model. And that was like one side that was like super interesting for me, like not the sad views, but it's really hard to see positive transfer. So it turned out to be a really, really good model, but it was like really hard to see that, wow, I train on images and then like text perplexity goes down. That was hard to see. Like the fact that, you train a native model and it's good at like across all the capabilities is already impressive. But my hope is that, multimodality and world model is the way to really push multimodal training to enable like positive transfer across modalities. I've worked with people that they were like expert on this, for example, one of the things that I remember that, at the beginning, they were talking about this like visual quality. And then I remember that, it's like, oh, this model is a great model. I send them, and there's like, no, this is not a good model. I was like, what do you mean? And they started showing me two images that to my eyes, they were like looking the same, but they were saying like, no, this is like way better. I was like, no, they're the same. So they had a good taste on grasping the visual quality of images. So working with them was like really interesting to kind of understand that, okay, there are dimensions. And by the way, like their intuition was the things that actually made like Nano Banana like a success in terms of, being a good product. But I was like, okay, what if we push this towards something beyond like traditional image generation? So instead of like a translator that, as you said, like a text to image, it becomes a thinking machine about images. For example, you enable interleaved text image generation, where the model can think in not only text token, but also in pixel space, right? So it generates text and then generates an image, and it generates another text, another image. And you can leverage that for different problems. Like one of them is that, if you have, like some sort of a story, right? Like, like text of the story, image related to that, text of a story, like, like children's storybook, right? Another one, which I was actually really excited about, was like this incremental generation. Like, let me just give you an example. So if you take like DALL-E or Imagine or standalone image model, right? If you ask these models to generate an image of like, a scene with 50 details, they might fail, right? And then someone can say that, okay, I can like generate a better model that like does up to 55 details. And then you say, okay, what about 60? And then I say, okay, let me just go back and train it and then come back to you to cover your case. But at the end of the day, there's a threshold that these models can kind of like follow instruction to some extent about, how many details that they capture from the text. But if you have incremental generation, so if you have text and then an image and text and image, you can get your model to generate these details one by one. So you never expect your model to generate an image, a perfect image in the first shot, right? So you expect your model to plan about this generation. So it says that, let me start with big objects, because, later I'm going to have a hard time if I put like small objects and the big objects don't fit, right? So let me just do that. And then like in the next turn, I go with like medium objects and smaller, and this like super smart, and you're never bottlenecked by the capability of a single shot image generation, because you did planning and then you tune every step difficulty to match the capability of your model to generate a one shot. So that was also one of the things that like, Nano Banana and native generation, interleave generation kind of brought like a completely new perspective to image generation work, which is like a little bit like far from like, just translating text into an image.
Fascinating. Does part of this contribute to efficiency? So especially Nano Banana 2, you have the flash aspect of this. So you're able to create amazing images very fast and apparently, seemingly very efficiently. So what's behind the scenes? Is that what you describe? Is that MOE? How are you able to do that?
First of all, I was involved in the original Nano Banana Pro. And then the last version, I again, like, because I jumped on the post-training and coding and agent, and I find it exciting. This one, like the team actually shipped it. But if I want to say like super high level that, what is exactly the things that makes the model like faster and more efficient, part of it is just the size of the model. So like Nano Banana was pro size, and this one is just like flash. So definitely the parameter size, like, configuration of the MOE and stuff. The other one was people actually spent quite a lot of time on figuring out like, like nailing down like distillation recipe, both on the side of like knowledge and like, other like things that basically you kind of like need to distill to something like a process that is like, lighter than the full process. Surprisingly, a lot of infra work for serving. So we have like really, really, really brilliant people that they're like, serving engineers. And it's kind of impressive that like you sit on your desk and then like they come and they say, oh, by the way, like casually, I made the model 10x faster. I was like, like it's just like, and they just kind of saying it like, in a very like, casual way. It's like, wow, this is like impressive. We had also a lot of work on optimizing the serving, how to serve these models. And like, again, like, because these models are operating differently from like, just like normal language model, like they're not necessarily, the same as, next token prediction. This is definitely something that, a good serving engineer can figure out that, okay, I can think about a different way of doing that. And we had also a lot of improvement on the efficiency side by their work.
All right. So as we get towards the end of this conversation, I thought it'd be fun to end with a few hot takes, if you're ready for them.
Yeah, absolutely.
All right. So what is one thing the AI field is getting wrong right now?
Not easy to pinpoint like specific things, but again, this is just like my personal opinion, and maybe I have colleagues and like the other people like sharing this with me. But I think we're underestimating how hard like jagged intelligence is to fix. We're missing how we're underestimating how much it matters. And we talk about almost like people laugh and go, like if you have a model that does like a very difficult like math proof, but has difficult time like counting like letters in a word. As I said, people just laugh and move on. But I think it actually like pointing at something like deep and unresolved about these systems, like the way that these systems kind of like represent and process knowledge. And it's not a bug that you can patch. So definitely, we see that, this is happening, like people sometimes, or we have these problems that, something is like awfully sad. And then you can, let me just patch by adding something to the system instruction or developer instruction. A bit of a structural property of how these models actually learn. So I would say this is probably one of the things that we're not getting it like super right at this point.
Great. What is one idea in AI research right now that is underrated?
Something that is underrated, like you mentioned, continual learning. I think this is definitely underrated. As I said, like sometimes the problem stays in the exploration mode until we are confident about something, and then it goes to the exploitation mode. I think we are past the time that we really had to push this to the exploitation. So maybe like foundation models are essentially right now like frozen in time. And like when the training ends, right? And then everything is like built on top of this frozen model, like RAG pipeline and fine-tuning workflows and retrieval system. And all these like elaborate like infrastructure is like all based on this assumption that these models are frozen. And it's a bit of too much of a strong problem. There's an assumption to make. And I think like we are going to like get to the point that we need to change these assumptions, and like maybe like we need to think about it a little bit more actively and have pushing it toward like, something that we actually push it to productionization. And maybe it's a little bit like underrated right now, like the continual learning.
So you think RAG goes away over time?
It's not going to look like as is today, and it's going to be different, but like saying that it's going to go away completely, I'm not sure about that. And one of the reasons that I say that is RAG is not just about bringing like fresh information to the model when it wants to kind of like solve a problem about like the current state of things, but it also has this kind of like in context learning. And there is a difference between in context learning, like the information that you have in the context of the model, compared to the information that you have in the weight of the model. Like continual learning and RAG are doing different things for bringing this fresh information. Maybe it changes in a way that, like it doesn't need to trigger RAG for like everything. But I'm pretty sure that there's going to be some tail of the distribution that we're going to do RAG still for it. Like what's the time?
All right, last couple of hot takes. What do you think people are too confident about?
So people think that, the pushing the technical side is sufficient. That if we just like get a model that is smarter, everything is going to follow. And in my opinion, like a version of AI that is like, really, really brilliant at like technical problems, but it has a blind spot about, everything else. And that version is not going to be able to actually create meaningful progress in the world. And the fact that, people kind of assume and confident about like they're confident about this, that kind of like, everything else is going to follow, or just everything else is just like a small list. I think it's wrong. Like, we have governance, we have like, regulation, we have social trust, we have like, for example, distribution of access and the benefit in the world for this technology. And even the the institutional capacity to kind of like absorb and adapt this technology is just like, this is something that maybe we don't have enough attention to. And these are not really soft problems. If not harder than the technical part, they're really hard. And like the pace of technical progress is definitely currently running ahead of the world's capacity to develop this kind of mechanism. And this gap is getting bigger and bigger. But what I'm saying is basically the field needs to hold both things at once. So maybe that's one of the things.
All right, and last one, and I don't know if that's a hot take or maybe just advice for anybody entering the field today. If you are going to start from scratch today, what would you work on?
I don't want to start from scratch. It's hard to start from scratch. I can tell you, there are two things that I think, would be nice to spend more time on it. And there's one thing that I'm very excited about it. I start from the things that I'm really excited about it. And I would say short term, it's really exciting to push it. I am actually trying to even be able to contribute to this direction. And that's full automation of super long horizon tasks. Things that, you have a machine working for maybe 2 weeks, 1 month. The agents today are very impressive, right? And the demos are very remarkable. But there's this compounding reliability problem that doesn't get talked about enough. And for example, imagine if an agent has to take 100 sequential steps to complete the task. And imagine if each step has 95% of success rate, which is great, given the models that we have today, 95% is really good. The probability of completing the whole task without a single failure is 0.95 to the power of 100, which is less than 1%. And this math is brutal, right? And this 95% per step, as I said, is very, very optimistic. Long horizon automation is it definitely isn't impossible, but it requires a level of per step reliability and error recovery, and the current system maybe don't have it. And if we want social trust and basically having people really using it, at the end of the day, people don't experience average performance of these models, then they experience the failures. If you have your model doing a dumb mistake, the damage in the trust that it makes is bigger than the benefit of getting 100 things right? 100 imperfect things right. So this reliability in this long horizon task is something that we definitely need. The kind of side of, as I said, two kind of more philosophical high level things. I would definitely work on grounding problem and how we can build AI systems that are robust and connected to physical world. As I said, soon, the concept of data, how to kind of enable these models to kind of be very good at self-improvement becomes how can I ground these models in real world. So this is definitely something that, would be the bottleneck of self-improvement if we don't actively think about it. We should definitely move away from this statistical pattern in text and pixels. And the other things that is maybe kind of related is even thinking about, a better definition of intelligence itself, right? And a little bit philosophical, but it's definitely a practical question. And the whole field and us, we're building more and more something that we haven't clearly defined. We're trying to kind of make these models smarter and more intelligent, but the definition of intelligent is just so hand-wavy and fuzzy that it's hard to actually kind of measure the meaningful progress. Which is related to your question that about how about evaluations. It's good, we have practices, benchmarks, scores, capabilities, and even vibes, which is I find super useful. But at the end of the day, we really need a systematic way of maybe defining intelligence that is hard. And again, making progress based on what we have right now is good. But at some point, that becomes a little bit more important to really pinpoint that, what is the target and what is the goal, and then push toward that with maximum speed.
All right, Mostafa, it's been a absolutely fantastic conversation. Thank you so much for spending time with us. Really enjoyed it. Really appreciate it. Thank you.
Yeah, thank you so much for having me. It was fun to chat, and thanks for the invite.
Hi, it's Matt Turck again. Thanks for listening to this episode of the Mad Podcast. If you enjoyed it, we'd be very grateful if you would consider subscribing if you haven't already, or leaving a positive review or comment on whichever platform you're watching this or listening to this episode from. This really helps us build the podcast and get great guests. Thanks, and see you at the next episode.